Bienvenue à tout le monde qui nous rejoint du Canada. Bienvenue au Cégep André Laurando. Et pour commencer cette présentation, je vais inviter notre partenaire local, Maroun, directeur général d'Optech, pour faire un petit mot de bienvenue avant de faire la présentation avec notre conférencier, Dr Daniel Reiner, aujourd'hui. Donc, Maroun, pour commencer en français, moi, je passerai en anglais par la suite.
Parfait. Bonjour tout le monde, bonjour aux gens qui sont en ligne. Donc, je suis Maroun, je suis le directeur général d'Optech, le centre de transfert de technologie qui est ici au Cégep André Laurando. J'invite tous les étudiants qui ne nous ont jamais visités de nous visiter en un petit rendez-vous, puis on organisera avec plaisir une visite de nos installations. Deux petites choses. C'est quoi qui m'a intéressé dans l'optique? Depuis que je suis au secondaire, je me disais comment on peut contrôler l'énergie la plus rapide de l'univers. Donc, je trouvais ça vraiment fascinant de trouver des méthodes pour manipuler de la lumière qui, vous le savez, est la source d'énergie, la chose connue la plus rapide de l'univers. Et en plus, dans un circuit photonique, comment prendre cette chose qui voyage extrêmement vite puis la contrôler sur des micromètres de dimension, des fois des nanomètres. Donc, on prend la chose qui voyage le plus rapidement dans l'univers, puis on essaye de la confiner, de la contrôler, de lui faire qu'est-ce qu'on veut dans un objet qui fait quelques microns en termes de dimension. Puis juste quand on pense à ces deux extrêmes, moi, ça me suffit pour me fasciner. Puis j'espère que la présentation va en faire autant. Bonne présentation.
Merci, Maroun. And so for those who are joining us online who are in English, maybe I'll just try and translate some of those words, Maroun, about the fascination that he had from secondary school to understand how the fastest thing in the universe, light, how that could be controlled at the smallest level of microns and nanometers, which is what we're talking about today on our subject of integrated photonic circuits. And so I have the pleasure to host here on behalf of the IEEE Photonic Society organization in Montreal, a local branch of the biggest organization for engineers in electrical and electronic engineering, but also in photonics across the world. We are hosting Dr. Daniel Renner, a distinguished lecturer of the Society, who will be talking to us about some of his career challenges and technical advancements in this field of photonic integrated circuits. I've had the pleasure of working with Daniel for a number of years at an international level of the IEEE, which was a network which I joined as a student when I was in first year of undergraduate, and which has literally taken me around the world from when I started in the UK to where I live now in Montreal in Canada. And with Daniel, we've worked in parallel on a number of projects for how do we engage the industry as part of these professional networks. But today, Daniel will tell us a little bit more about a hot topic that's exciting the area for which we will need much more energies, many new ideas, and many more people to be able to fill it. So without further ado, Daniel, the floor is yours to talk about monolithic, heterogeneous, and hybrid photonic integration, and exploring how this is a role for all. So, Daniel, over to you.
Thank you, Matt. C'est un plaisir d'être ici aujourd'hui avec vous. That's the extent of my French. I apologize, but the rest of the talk will be in English. I hope everybody can follow. If you can't, please let me know. I'll do my best. So, as Matt mentioned, the topic of conversation for today is photonic integration. So I don't know if most of you have heard that term. I'm sure you've heard about electronic integration, electronic integrated circuits, where you have many electronic components all in a single chip, an IC. There is a similar concept in photonics, where instead of having electronic devices all in a single chip, you have photonic devices all in a single chip or something like that, where you can have lasers, optical modulators, and et cetera, all in a single chip. So that's the topic of conversation for today. And how do I change from one to the next? Maybe if I press here. Which one is it then? Oh,
I think it was not on the right area.
okay. All right. So perfect. So what we're going to do, we're going to talk then about photonic integration. And this is a little different to what maybe in the past you've seen. It's a technical talk, but not entirely. It's a talk that also incorporates some business elements. And that's an area where I've been for the past 30 years or something, where business and technology get together. So a little bit about why is photonic integration as it is. The reasons why it is are mainly business reasons, not entirely. They're technical, so we'll explore both. So we'll start with photonic integration. What are the drivers for photonic integration? And very important, what are the similarities and differences between photonic integration and electronic integration, as we were pointing out earlier, sorry. And then we'll go into some selected examples of integration. This is an area that has been developed for many decades now. So there are many, many examples. There are many, many ways within the 40 minutes or so that we have. Obviously, we cannot go everywhere, but I've selected a few examples that I can give you an idea of the different options that there are for integration. And these different types of integration basically fall into three different categories. There is monolithic integration, which is where, just like in an integrated circuit, which is all in silicon, in a single silicon chip, monolithic integration means placing all of the photonic components, a laser, as I say, a modulator, whatever it is, all in a single crystal, in a single chip. Or heterogeneous integration, which is where you still have a single chip, but that has been made in separate parts and combined at the end into a single chip. So it's kind of monolithic, but not entirely, because you follow two paths, or sometimes three or more, to make different parts of the chip, and you kind of put them all into a single block at the end. And the third category is hybrid integration, which is a situation where you have different elements, they are separate, and you put them together by placing them in a common substrate, for example, or also could be some degree of placing them all in a single chip, but not as intimately together as in the heterogeneous integration. There are some examples that could fall in either category. They are somewhere in between. It's a spectrum of different ways of integrating rather than three distinct categories. But in general, these are three different categories of photonic integration: monolithic, heterogeneous, and hybrid. And we'll talk about examples of this. And then we will end up with, well, this is where we are right now. How do we see the future developing? And that's always very difficult. So we'll go through that very fast, and you'll forget what I said. No, I'm just kidding. It's important to go into defining what the future, and I'm probably going to be wrong, but you'll forgive me when you look at it 10 years from now. So as I say, if we look at it from a business perspective, this is one sort of analysis of what the photonic business looks like. And it says that the global photonic component revenues are of the order of, give or take, $300 billion a year. That is a big number. That's a huge number. But what you have to understand is that a lot of things fall in that category of photonic components. There are things in this list here. If you look at power, it says laser welders, directed energy weapons. We're all familiar with LEDs for illumination. These are all photonic components. The LEDs that today provide you with light is a photonic component, but it's not an integrated circuit. So actually, the vast majority of these $300 billion of photonic components are not integrated circuits. The vast majority, actually the proportion of integrated circuits that today, photonic integrated circuits, of those 300 billion is a tiny number, or relatively tiny. It's not that tiny, but we can look at it here. So these are other estimates produced by marketing companies. And if you look at the right side picture, you can see that at this time, this is a projection to 2025, but okay, we're in 2024. The silicon photonic market is of the order of 3 to 4 billion, somewhere there. All of these numbers you have to take with a pinch of salt. It's an order of magnitude. So out of the 300 billion that I was mentioning before, silicon integrated circuit, photonic silicon integrated circuit are something like 4 billion. If you look at the, also say the approximately now, this is 2025 transceiver market, it says there the total transceiver market is 17, 18 billion dollars. So if you take these numbers and you say, well, what is the size of the photonic integrated circuit market for the components today? Well, it's somewhere between those numbers, somewhere between 4 and 18 billion dollars. Let's say, for the sake of our argument, a round number, 10 billion. That is the size of the photonic integrated circuit market these days. And $10 billion is a lot of money. I don't want to argue that it isn't. It's a very nice, large number. But I want you to remember that number, $10 billion, as, say, approximately the market for photonic integrated circuit these days, because we're going to compare it with the electronic integrated circuit market. And as you can see, that's 2021, $600 billion for electronic. Remember, 10 billion, now 600, growing to 1 tera billion in 2030, 1,000 billion. So today, that's 2024, let's say somewhere in between is $800 billion for the electronic IC market. So the photonic, and this is an important distinction. This explains a lot of what follows here afterwards. Photonic integrated circuit market today, about 10 billion. Electronic IC market, 800 billion. It's basically 2 orders or 100 times, two orders of magnitude difference. And so this just, it's a huge mammoth monster next to a big market, but in comparison, it's a tiny thing. And when you are in photonics, like I am, I mean, you tend to think, oh, $10 billion, that's a really big market, nice market. But sometimes it's important to look a little bit outside of your comfort zone, a little bit outside and look at these numbers to realize where really you are. And actually, I live in California, in the United States. I mentioned I have actually a daughter and grandchildren that live in Montreal, so I have a family in Montreal. But I live and work in the United States, so I'm familiar with what happens there a lot more than what happens in Canada. But I don't know, some of you might have heard in the United States, a law was passed a couple of years back, the CHIPS Act, that is supposed to, and it is, funding development of chips in the United States, electronic and photonic. And basically the funds going into electronic and photonic split more or less in this mode. So it's mostly for electronic chip development and manufacture, and some for photonic chip development and manufacture. So basically, you also might hear, sometimes it's in the news, a new silicon wafer, a CMOS wafer fab, costs billions of dollars. Cost of a fab is, old numbers used to be like 5 billion. I think now it's 10 billion and more. And that, say, if you invest in a fab, in a silicon fab, $10 billion, and your market is 800 billion, obviously it's something that makes sense. But like in photonics, if your market is 10 billion, you cannot invest $10 billion. So that's you're starting to see how the two are very different, and what we think for one cannot be applied to the other. The difference in money that you can spend in capital and also in developing a product, it's always about a factor of 100. It's somewhere between 20 and 100, the differences in what you can spend. So PIC markets are significantly smaller than electronic IC markets, main difference. And in addition, if that wasn't enough of an issue, a differentiating factor, photonic integration technology differs from electronic integrated in that it involves a variety of dissimilar materials. So we have 3,5 semiconductors, that's indium phosphide, gallium arsenide, gallium nitride, etc. Group 4 semiconductors, silicon, germanium, tin. In general, electronic ICs are based on one material, vastly, that's silicon. We do use silicon in photonics, but it's only one out of many different materials. And here I mentioned some others. And this is because the applications for photonics, which span different wavelength ranges, for example, there are photonic devices that emit in the visible, like the lighting that we have here, others in the infrared, others in the far infrared, or need to detect in the far infrared, or in the ultraviolet. All of these things need, any wavelength range that you look at requires a different material, and that's kind of why we need it. Silicon doesn't address unfortunately, every single photonic need. In addition, silicon is a rather bad material, if not impossible material to make emitters, lasers, for various reasons that you will learn once you go. I think most of you will go to university and you'll learn why you cannot make lasers, dot lasers out of silicon, but that's a big problem. You cannot make lasers out of silicon, or it's very difficult to say. There are many materials, there are many components that go into photonic integrated circuits. In an electronic integrated circuits, you need to make transistors, diode, resistors, and capacitors, pretty much. That's it. The 4 components, you're mostly, I don't want to oversimplify, but that's pretty much it. Whereas in photonics, here we have this long laundry list of different components that you need to make. So lasers, amplifiers, LEDs, photodetectors, modulators, waveguides, etc., etc., etc. Fortunately, not every photonic integrated circuit needs all of them, but typically several of them. So extremely complex. And in addition, PIC packaging is also more complex. In electronic ICs, to connect it to the outside world, you're connecting it essentially mechanically. You need to hold it somehow, and thermally, you need to take the heat somewhere away, and electrically. In the photonic packaging components, you have all of those. Plus, you need to connect it optically. Either light needs to go out or come in. And that also, in general, is quite complex. So we have a situation where we have a technology that is orders of magnitude more complex than in electronics, and orders of magnitude smaller market. It's a double whammy than in electronics. So why bother? Okay, forget it. Let's not get into that. But the thing is that the business drivers for photonic integration are still there. There are advantages in integrating because of performance. Sometimes you get advantages of speed, for example, that otherwise you wouldn't get. Cost, size, weight, and power is always important in making things smaller, lighter, cheaper. It's always important. So also what's become quite important is adding photonic components to electronic ICs. So what we're seeing now, and this is really a great vehicle to get larger density photonic integration, is really an electronic photonic IC, where both types of components are in a single chip. So all of these are drivers to still go ahead with integration. All I'm saying here is that you can only take the electronic integration path that is older, that started earlier, that is going 30 years ahead. You can take emulating that only to a certain point. In fact, to a very sort of low point, because beyond that, it's totally different. And the path then to implement photonic integration is not the same as in electronic integration, which by and large is monolithic. You still can consider monolithic if that makes sense, but you need to seriously consider heterogeneous and hybrid if that makes sense, or a combination of the above. So we've already talked about what hybrid, heterogeneous, and monolithic integration is about. And what we're going to discuss now in some detail is, as I say, some examples. And here I don't want to be exhaustive, just to give you an idea of monolithic, heterogeneous, or hybrid integration. So in this slide, we have a very simple example of a photonic integrated circuit. So it consists of two elements, basically a laser, and it's a particular kind of laser called an amplifier. So this already is a photonic integrated circuit. It's as simple as you can get. There's more than one component. There are two components. So I started with the simplest thing that there is. But actually, having two components in a single chip gives you advantages. One, because you have a separate amplifier, you can get higher powers. In this particular case, this laser can generate hundreds of milliwatt, which for a diode laser is high power. And because the amplifier is separate from the laser, as you change the power, and this is shown here, this shows if you only have a laser, as you change the current from the laser, you're heating it up, and that changes the wavelength. Sometimes you want that. You want to be able to tune the laser with current. Sometimes you don't want that. You want the wavelength to be stable as you change the power of the laser. So in situations like that, an approach like this is what gives you the answer. This is the wavelength as you change the power by changing the current in the amplifier rather than through the laser. So this is a simple example of something that easily can be, well, nothing is easy, sorry, forget the word easily, which can relatively easily be done because it's only two components, but just by integrating in this case, you can get some advantages that otherwise you wouldn't have. So then the complexity can increase. This is a single chip that the block diagram is shown on the upper left. A scanning electron microscope or micrograph of the chip is shown on the top right. And in this case, a tunable laser, actually in this case, consists of actually four elements. There are four elements there are two mirrors, a gain section, and a phase section. So there are four elements in the tunable laser: an amplifier, that's the SOA, a modulator. So there are 6 elements in each one of those lines. Then there are 4 lines. Basically, what that is 4 tunable lasers where you can adjust the wavelength, followed by amplifier, followed by modulator. You can modulate the 4 separately. But there are already 24 components there. And at the end, a combiner. So in that chip, there are 25 components. So you can see this is significantly more complex than the device where there were 2 components. But I would say, I mean, this actually is before sort of semi-retiring, I worked for this company, Freedom Photonics. So this is something that we did at Freedom, I don't know, about 8 years ago. And at the time, and I think still to some extent, is one of the sort of turning points of photonic integration. So what I want to highlight here is that in an electronic integrated circuit, you can have millions of components in a single chip, as you've heard, I'm sure, many times. In a photonic integrated circuit, the numbers in general are relatively significantly lower. As I say, in this case, by orders of magnitude lower. There are some photonic integrated circuits that have million components, like, for example, the imager in your digital camera. As you've seen many times, I'm sure you've seen it has, I don't know, 10 megapixels or whatever the number is, some megapixels. But if it's a 10 megapixel camera, that means that there are 10 million photodiodes in a single chip. In that case, well, there are 10 million photonic components in a single chip. So that is a particular case of a photonic chip that has a number of components that is comparable to electronic integrated circuit, but they're all exactly the same. They're not different. So you have 10 million components, all the same, or at least the hope is that they're all the same. There are a few that are always sort of, there are a few failures in any imaging device. You allow for a few failures here and there, but that is a situation where you can have devices at that level. But by and large, a photonic integrated circuit will not be as highly integrated as an electronic circuit, and that is to some extent because of the cost of developing a very highly integrated chip that, as you mentioned earlier, you cannot afford. So, okay, you are happier with smaller, and the rest you hybridize somehow, like it's shown in this package here. So we have the block diagram, this is the micrograph, this chip is here in this package. And the chip, the output out of the combiner that has the optical output, then goes to a series of optical elements and then out into the fiber. And prior to the chip, there is circuitry, and there, as you can see, everything repeats 4 times. So there are 4 circuits entirely the same, each one connected to one of the tunable lasers there that control the temperature, the output power, and the wavelength. So these are control circuits. And if you want, if you look at this, you can consider this as something that is hybridly integrated. So the chip is monolithic, but the combination, the whole 4-way transmitter, is a hybrid. So this is the approach that you have to follow in order to get into integration of components. This here is also a case of a 2-component device. In this case, it's a laser followed by a power amplifier. So this is the laser, or sometimes called a master oscillator. This is the amplifier, and it's a laser followed by an amplifier so that you can get to very high powers. In this case, it's possible to get to watts, several watts of output power. And we talked earlier about integrating electronic and photonic components. So this is the situation of having an integrated circuit. In this particular case is so if you have a camera, as I said earlier, and you have a huge number of pixels, say more than 10 megapixels, and you want to, this is not a photographic camera, this is a video camera, so you have many frames per second. You're generating massive information out of so many pixels, and if you're changing frames, you're getting a new frame in a fraction of a second. So you're reading that array of photodiodes with an integrated circuit that is right behind, which is here, and then you need to extract to the outside world whatever the readout, the reading IC is reading. And so many times you need many gigabit, tens of gigabit, sometimes 100 gigabits or more of transmission power out of the integrated circuit, which really, it's not the only way, but the most effective way of doing it is optically. So the way this is done is by having, these are ring resonator, which work as modulators in this case. So you have modulators that are built into the integrated circuit that modulate light. So you have lasers in the outside world that pump light into the circuit where it's modulated, different wavelengths. Actually, I mean, each modulator addresses a different wavelengths, and you receive it again in the outside world. So this is an example of somewhere where combining electronic and photonic components, you can achieve goals that you cannot otherwise. And this is something that is sort of becoming commercial and is in the process of transition, and which is revolutionizing the ins and outs of integrated circuits. So Intel, for example, has been working on this, which is essentially the same concept, where in a chip we have a laser, 4 micro ring resonators, detectors, and an amplifier. So again, the idea is very similar of getting light into the chip and then modulating the light and getting the information out. This is another example, and this is an example of sort of in your digital camera. Obviously, your photodiodes are sensitive to visible radiation. Many times you want to look at infrared for various reasons. But it's the same thing. You're taking a picture, but in the infrared. So one of the problems of getting a picture with infrared is that then again you need special materials. You cannot use silicon. You get into materials that are very expensive, very sophisticated. The wafers are small. So this company, Illuma, has developed a way of growing these very expensive materials, but on silicon. So you can share all the capital, very expensive, that have been developed for fabricate infrared detectors, arrays. Once you get that, as I mentioned, you need to couple your array to a readout integrated circuit. So you can do this at wafer level. You can attach wafer to wafer. So you're processing many arrays at the same time, which again makes it easier and faster and cheaper to do. Also, it is possible to integrate monolithically lasers, in this case, or photodiodes onto the integrated circuit itself. So you can grow 3-5 semiconductors, for example, onto the silicon wafer selectively, so that you only grow it where you need the laser or the photodiode. And this is an example of actually a 12-inch silicon photonic wafer where the devices have been grown and processed on top. This is sort of 12-inch, so it's a wafer about this size, which is totally unachievable in any other way. One other technique, and this is by another company, I always have the companies somewhere there that we, in this case, it's a technique where actually it's you make photodiodes by what's called colloidal quantum dots. So essentially, you spread a polymer that contains these dots over the wafer that define the photodiodes. So it's a relatively inexpensive way. Rather than growing and processing the crystal material, you just kind of spread the layer on top of the crystal to define the photodiodes. So all of that about different examples to give you different ideas of all that's done in monolithic integration. Now, heterogeneous integration, and this is by a company called Nexus. So as I mentioned here, there's an example of a photonic integrated circuit. As you can see, there are a number of different complex components. There are lasers, amplifiers, various waveguides, couplers, and so on and so forth. And here, the passive components are all defined using silicon nitride on silicon, and the actives, lasers, and so on are fabricated separately and then integrated through different kinds of bonding together. This is what I mentioned before. You fabricate the thing separately and you integrate that. So this is an example of heterogeneous integration. Here, there's another example of heterogeneous integration. This is a lithium niobate chip. This is technology that's been developed recently, where you can make good modulators and also waveguides in lithium niobate. And then you add the active components, the lasers, heterogeneously. Hybrid integration. So here, as I mentioned, you might want to have some separate devices on an optical bed on a carrier. So in this case, there is an active device like a laser, for example. And here there could be a modulator or some other component. And just like in wire bonding, electric wire bonding, you define a waveguide between the two components that can carry the light. It's an optical waveguide that provides an optical wire bond then rather than an electrical one between two components. This is defined through a method that is essentially something like a three-dimensional photolithography. You define the waveguide in 3 dimensions. The same method can be used to define lenses, mirrors, reflectors. These are all tiny components that are defined using the same methodology that I showed you before. This is another way of hybridizing, which is from this company called ICAP, where they can define waveguides, like shown here, where the waveguides form a splitter. So you have light coming on the left that is split into 4 on the right, and then you can attach something. There's a method of attachment where you can attach, say, a fiber or another component to the glass waveguide element, and you can attach another component or fiber to, say, the other side. So, for example, you could have a fiber attached here that brings light from the laser, and on this side you can have an array of 4 modulators, for example, or any other such combination. So that would be also an example of hybrid integration. Polymers have been used. This is actually a company that develops modulators based on polymers. Polymers are relatively easy to use in integration. There are some issues with them related to reliability and so on, but they're easy to implement. So that, and again, I only wanted to cover a limited range. If you're interested in this, the world is infinite. You should study photonics and photonic integration, and there are infinite number of examples of different ways of integrating. And this is something that obviously, as I mentioned, I hope I wasn't too negative to start with. It's a balance. I mentioned the reasons why there is a need for integration, and those needs will grow, but there are limitants, which is what I mentioned earlier. But driving things to the future are quantum 2 applications. I don't know if you've heard, but obviously a laser is a quantum device. There's the so-called now quantum 1 generation, and a laser in general is part of quantum 1. There are now new kinds of devices, the second wave of quantum devices, quantum 2, that are devices and systems that are finding applications essentially in 3 areas: in sensors, quantum communications, and quantum computing. And this will require a large number of single devices and PICs. So this again shows a market perspective. And again, the numbers are billions, not hundreds of billions and so on, but still it's a big market for photonic components. This will require, these are some devices or systems that are needed for sensing, communications, and computing. And this will need a variety of different lasers, some specific kinds of lasers. Many specific wavelengths are needed to excite atoms and such. Single photon sources, single photon detectors, and so on. A number of components that are pretty unique. I am not going to go through all the details of this, but this is going to be posted by the IEEE. So if you're interested, obviously have a look at that, and you can always contact me as well. But this is, again, an example of a photonic integrated circuit for quantum applications, including some of the devices that were shown earlier. Again, some of them showing the status of development of quantum devices. And there's no question that quantum applications will materialize, probably not next year. Some of them are materializing, but not in volume for another 5 or 10 years. But that's a good timing for when you will be entering the workforce. So it's something to keep in mind. The issue with quantum devices is that there is a very high technical risk at this point, and There's only so much that commercial industry can do. So in many countries, there is a lot of government funding that is going into quantum. And going forward for quantum 1, as I mentioned, big markets are relatively small. Fabrication and packaging technology is complex, but we still can integrate, but we have to be very clever about it with a careful balance of monolithic, heterogeneous, and hybrid approaches. And also leveraging silicon electronic IC technology when possible. There are many times where this can be leveraged. And so you need to be very choosy about your path. And quantum 2 PICs, actually the applications many times are even lower volume than in quantum 1 and requiring even more complex PICs. So we're looking at a time when the development and commercialization of PICs need a paradigm shift. Essentially looking at ways, how can we make components at low volume and still at a cost that is reasonable? It won't be low cost, but at a reasonable cost for the application. And there are many ways, again, to do this. It requires a lot of understanding of the market and understanding of the technology. And actually, you're the generation that will bring this into fruition. And I am fully confident of that. And I thank you, and it's been a pleasure to be here.